Oh, thank you, computer. Okay, well, thank you everyone for coming along. Welcome to the first inaugural session of the Simulation Summer School, which is being arranged in part by SciPAG, the Psychology Postgraduate Affairs Group, and the Maths, Statistical and Computing Psychology section from the BPS. I'm really happy to have Lisa DeBruine here to talk about Faux, which is a package that helps us simulate data. Lisa is a professor at Glasgow University and specializes in evolutionary facial recognition and also like teaching R as a complete brilliant R teacher and things like that. Does a lot in the R learning community. So I'm going to move over to Lisa now and we'll get started. Thanks.
All right, thanks so much. I'm really excited that I get to be the first one for this series. Such a cool series. All right, so I'm going to, what am I doing here? Okay, let me put into the chat one more time the, well, now that I'm screen sharing the chat, it's harder to find. Okay, now it's over here. Oh, all right, what is this? There we go. Okay, so there's a web page here that contains all the materials that we're going to go over today. And at the top of that web page, there is a function to install a development package. It just gives you all of the other R packages we'll be using and the files for today. But if for some reason that's not working for you, actually, I'll just pop this over here so you can see. Okay, so we run that code to install, and then you can just use these two lines to get the RMD files that we'll be working on today. But if that's not working, then you can download the first file we're going to work on. It's Faux stub. If you click on it, it might look like this, and then you need to like save it as a .rmd file. If you're on a PC, this is somehow a nightmare to save files. Then you could instead just copy everything and paste it into an RMD file. So there's our multiple ways to do this. So what I would recommend, hopefully everybody's got RStudio open. If you don't feel like following along, that's fine. All these materials are going to be available to you forever. So but I would recommend start yourself a new project in like simulations. You can keep coming back to these and keep all your stuff in there and create a project. All right, and then if you've run that one already, then you'll have the data sim workshop stuff. Then if you just run this, so it'll give you a package called DSW for data sim workshop, : exercise, and then in quotes Faux. So let me make this a bit bigger. So if you guys put stuff in the chat, if you have questions, want me to speed up, slow down, whatever, put it in the chat. And then if I'm ignoring the chat because it's on the screen over here, you can just turn on your microphone and yell at me, or Oliver will do that, I guess. So let me know if things are like too small to see or not in the right part of the screen or whatever. Okay. If you have no package called DSW, did you install it? You need to install it first with this code. Oops. Okay. So, all right, so it'll do this. And then don't update anything. This new fancy package might take a little while, so I just don't update anything. You probably don't need anything updated, and then it's done. So, and then we do exercises. If this doesn't work for you, for any reason, just go to the page that I've put in the chat here. And again, that will just show you this. And then you can save it as faux.stub.rmd, put it somewhere where you can find it, open it up. Or if that for some reason isn't working, select everything, copy it, pop back in here, make a new R Markdown document. Just click OK, delete everything, and paste it in there, okay? So those will be the ways that you can access this. People keep coming in. Oliver, can you like private chat them and give them the links? Thanks. Okay. So, oh no, okay. Ava's stuck in updates. Yes, and if you don't have remotes, DevTools also works. I'm not gonna save that one here. So, but you might not have DevTools either. So you might have to install one or the other of those to be able to install something from GitHub. And again, if that's a bit of a rigmarole for you, just download it straight from the webpage. All right. So we're gonna, while everybody's doing that, those of you who already have it loaded and have gotten now Faux stub up as an RMD file, I'll show you a few, orient you to a few things on RStudio. So there's this wee thing, what is it called? The document outline. So Shift Command O, or if you just click on this, will show you the outline of this document. And that's really useful for jumping around to things like different exercises and different parts of this document. And hopefully you're able to knit. This will just knit to a HTML. So if you just click knit, the exercises aren't filled in, but everything else is filled in. It will just run all this code for you. If you can't run the code, that'll mean that you haven't got something installed probably, and it might prompt you to install a package. Let's see. And then once you knit, you'll have this, this document here. So all of the intro stuff that we're gonna go through today, plus a bunch of exercises. Okay, I'm going to stop worrying about people who've come in late, and they will just have to catch themselves up at some point. So we're just gonna start in on this file. So if you haven't worked with RMD files much, they're a really nice way to have our code chunks. So you have a chunk like this, it starts with 3 backticks and open curly brackets, the letter R, and then sometimes there's some extra info and close curly brackets. And then they end with 3 backticks. So you'll see this kind of gray or different color code chunk or block. And you can put our code in there, and it's just normal R code. So this gives us some knitter options that control how it's knit when you turn it into an HTML document. And I'm setting the seed to my favorite seed. That's just if you run the whole thing, then everybody will get the same numbers here. But we don't need to worry about running that when we're going through interactively. So this code chunk loads our libraries. We're gonna load the Tidyverse library, Faux, Broom, and Apex. Tidyverse is just for data visualization and data wrangling. Faux is what we're gonna learn today. Broom helps us turn analyses like t-tests or ANOVAs into a table, which is really useful for data simulation. And then Apex, because we're gonna do some ANOVAs. So if you wanna run a whole code chunk, you can click on this little green arrow. That will run everything. All right, so yeah, do that. But if you're inside of a code chunk, you can also just put your cursor there and hit Command Enter to run just that one line, and then it pops down to the next line. So we'll do kind of either of those as we go through. All right. So the first thing I'm going to teach you how to use is the Arnor Multi. I don't know if people have used Arnor much. Okay, there's a keyboard shortcut to do this, but if you want to make a new code chunk, you can type that stuff in, which is a pain, or click on this little button, click R. I can't tell you what the keyboard shortcut is because I can do it with my fingers if I'm not thinking about it, and the second I think about it, it's gone. I can't do it anymore. I don't know what it is. So just use this thing or you figure out for yourself what your keyboard shortcut is. Okay, so I have people who have hopefully used Arnor before. This generates a random normal, just or gives you values from a random normal distribution. So our first argument here is n. So let's get 10 values from a random normal distribution with, oh, sorry, every time somebody enters the waiting room, it takes over my screen and I have to like click back into RStudio, which you guys probably can't see. All right. So we have to say what's the mean of our normal distribution. It defaults to 0, but we're just going to type it in, and the standard deviation. So those are the two parameters that we need to simulate a normal distribution. All we need to know about it is the mean and the standard deviation. And then we say we want 10 values. So you can run that. Just click that button there. And here we've got 10 values from a random normal distribution. Grab another 10, another 10. All right, hopefully most of you have done something like that before. But if you want 2 sets of values that have a specific correlation to each other, there's a function for that in the mass package that you can use, and you have to set up some other values by multiplying kind of the matrix of the correlation matrix by the standard deviations. And for 2 things, it's kind of straightforward. And for 3 things, it's a little bit harder. And for 5 things, it's just like, you're never going to get it right in the first try. So we wrote a function called Arnor Multi, which lets you have any number of correlated vectors, and you can set them up in this way, right? So Arnor Multi takes, it's much like Arnor, takes an n, so we want 50 values. We want 3 variables here, not just 1. And then we can say, what are their means? So we want their means to be 1, 2, and 3. And their standard deviations, 0.5, 1, and 1.5. And their correlations. So here, because there's 3 things, there's 3 correlations, the correlation between 1 and 2, 1 and 3, and 2 and 3. We'll go over how you set correlations a little later. And then what do we want to name these variables? A, B, and C. So if I run that whole chunk, this creates in our environment a data table. Let's have a quick look at it. So it's got these values A, B, and C. And let's check that they have the parameters that we simulated. There's a function in Faux called getParams, and it's just, I like to run it to make sure that stuff is set up the way I thought I set it up. This one's pretty straightforward, but when you have more variables, it gets a little bit more complicated sometimes. So if you run getParams, you just get a little table, and because they're sampled, you won't have exactly 1, 2, and 3 as the means, and 0.5, 1, and 1.5 as the standard deviations. You'll be close to that, the bigger your n is. But every time you run this, you'll get a slightly different sample. So this just gives you the n for each of your, well, it's 50 for each of them. And then what your variable names are, and then across the top, those same variable names and their correlations. So this is just our correlation matrix. And then means and standard deviations. All right, so again, that was the sampled. So we've sampled these values from a population where the means are 1, 2, and 3, and the standard deviations are what we set in the correlations. But we can set a flag or an argument called empirical to true. And that means the values are now the sample parameters. So your sample will have exactly those parameters. And that's sometimes useful. So same code as before, but now empirical equals true. And when we get the parameters, they're exactly what we specified. And sometimes if you're simulating data without a very large n, and you want to check, like, does this table look like what you expected? You might have specified the correlations in a kind of tricky way that makes it hard to know what this would look like. You might want to set it to empirical, check, okay, my correlation matrix is right, and then set that back to false for your actual samples. Okay, there's some shortcuts you can use here. So actually type in the chat. Let's see if you can guess how these work. So guess 1, we've got Arnor Multi 50, mu equals, actually this normally fits on one line. Let's shrink that over there. Okay, x equals 1, y equals 2, z equals 3, empirical true. So, and then we're gonna run that. So Can anyone guess like what the shortcut is here? You can type in the chat. All right, so variable names are implied in the mean array. Yep, they all have the same standard deviation. So we didn't set any values for the correlation, so they all default to 0. We didn't set a value for the standard deviation, so they all default to 1. We set the means, and if you use a named vector here, so if there's names in the vector, X, Y, and Z, it'll use those names. You don't have to set var names specifically. You can set them. If you do set them, they'll override any names that are in the vectors. But if there is no var names and any of your vectors have a name, it'll use those names. Second shortcut. So the first, we didn't put n equals, the first argument is n for almost all random variable stuff, so I just didn't name it. So we want 4 variables, r equals 0.5. So we've only got one number there. All right, yep, so, yep. So if we only set r to one number, that will be the correlation between every pair of variables. Perfect. Okay. Here, we're going to take the iris data set, just columns 1 through 4. So if you're in an R chunk, if you highlight a bit of code and then press Command Enter, it runs just that highlighted bit of code. So this is the columns 1 through 4 of the iris data set that's built into everybody's R. So sepal length, sepal width, petal length, petal width. So we're going to calculate the correlation matrix. So if you want to look at that, it's enormous, but it's that matrix of all ones across the diagonal. It's a symmetric matrix. We're going to calculate all of the means and standard deviations. So all the mu's, all the SDs. And then we can use those in Arnor Multi. So now we're going to simulate 50 values with the same mu's, the same standard deviations, and the same correlation. So if you have a correlation matrix created by core, you can just use that. Again, these are really big. So yeah, shrink that down a bit so you can see it. All right, so then we get, again, a correlation matrix that's pretty much like the original data set. So that's one other way that you can set the R is with a correlation matrix that you either create yourself if you know how to create a matrix, or more likely that you've run some pilot data, you've got the correlation matrix from core anyways, and then you can just use that. All right, so again, if all the correlations are the same value, then we just set R to that value and they'll all set to that. If it's a vector, you can also set it as a vector or a matrix. So this is how you would make the full correlation matrix as a vector. So this isn't a matrix data type, but it's just all 16 values here. I've set it up like with line breaks so that it looks like a matrix, but this isn't itself a matrix. So then we could use that as the row. And that gives us, oops, I'll shrink it down a bit here. So again, that same correlations. Or you can be a little bit lazier and just specify the upper right triangle. Like, because the lower left triangle is got to be like, these two have to be the same value. These two have to be the same value. So why do you have to put them both in? And the diagonal is always 1. If it's not 1, something's gone wrong. So just do the upper right triangle here. So just these values. So that's why if you have 2 variables, there's only 1 correlation that you can specify. If you have 2 variables or 3 variables, there's 3 correlations. One between 1 and 2, 1 and 3, and 2 and 3. If you have 4, then there's 6, and it continues to increase. So you just specify those, and then you'll get the correct correlation matrix. Okay. So again, this expands up to any number of correlations. I have before had to simulate something, trying to do power analyses to replicate a paper where there were like 20 different values. I got that from the original paper, like they printed out the correlation matrix of their data, and that was all the information I had. Sometimes you can run into impossible numbers that, like, let's say we try to give this a value of -0.9. I don't think this is going to work. Like it's literally not a possible correlation matrix. And then you get this error, correlation matrix not positive definite. And like you can't do that. And then you need to, so if you're making up correlation matrices, sometimes you can make up an impossible one. If you are trying to run a correlation matrix that's from a published paper and it tells you that it's impossible, then you start looking at what's going on with this paper. All right, so this is for our correlated, normally distributed, continuous variables. But the main thing that Faux really does is simulate factorial designs. So there's another function called Arnor Multi, it's called SimDesign. And SimDesign takes parameters. If anybody's used AFEX, the parameters are a lot like AFEX's between and within subject variables. But if you just run SimDesign itself, it defaults to an n of 100 observations of a single variable. The variable is going to be called y by default, but you can change that. And it's going to be your dependent variable of the mean is 0, standard deviation 1. So just do that, and it will plot this for you. It will plot where the mean is, like the mean you specified, and the standard deviation you specified. You can set plot equals false if you don't like the plots, but we're going to use the plots today. All right, and then we pop into our environment here. So you guys are on top of the environment. What did I call that one? SimData1. So you end up having an ID. So there's an ID for each person. The IDs have an S in front of them, and that is just because that totally stops you from accidentally using it as a continuous variable in any analyses, and why. All right, but we can give our factorial design between and within subjects factors. We're going to work with this pet time design a bit here. I'm not entirely sure what the pets are doing, but there's cats and dogs and ferrets. And so you can't be both or switch from one to another. So it's a between subjects variable. We set it up as a list because you can have more than one. So we only have one, and its name is pet, and then it equals the levels, cat, dog, and ferret. And we have a within subject variable in this design of time, and its levels are pre and post. Right? So you can set that, and then here's our pet time design. Everybody's still got means of 0, standard deviations of 1, but it gives you a plot so you can check, like, does that look like it makes sense? We have cats, dogs, ferrets, pre and post. So now we can set mu. You can set it with an unnamed vector. This can get tricky, like which one is it? Oh no, cat dog. I feel like I do need to, I've heard about this cat dog a few times recently. All right, so what this does is, so cat pre, cat post, dog pre, dog post, ferret pre, ferret post. Those are the 1 through 6. I always get confused when I'm trying to set my parameters with an unnamed vector. And I often do something like this first. Be like, okay, yeah, that's the first one, that's the second one, that's the third one. And then I'll change that to the actual numbers that I want, just to figure out like what order are they supposed to go in. Because if you have more than, actually it would make more sense to have this here. Because the order that they go in is 1, 2, 3, 4, 5, 6. And that makes sense to me. So again, like changing the order of between and within here doesn't matter as long as we've named them. But you're not stuck. There's a few different ways to set μ's and standard deviation. So you can set μ's by category or by level for just one of your variables. So I could set the μ's for all the cats at 1, all the ferrets at 5, all the dogs at 3, and standard deviation for everything that's pre at 1 and post at 2. So that would look like this. So here you can see they're out of order: cat, ferret, dog, 1, 5, 3. But so it doesn't matter what order they're in if you've named them. Or you can do this as a data frame. So you can set up a data frame with row names. If I just run this data frame here, it looks like that. So pre, post, cat, dog, ferret. It doesn't matter what order those are in. It doesn't matter if the within or between subjects are the rows or the columns. As long as you haven't done something weird like have your between and within subjects variables have the exact same levels, then it'll decide. I don't remember what it will decide, but you'll have to have a look and see. It'll just sort of pick one as the between and one as the within. In the very rare circumstance where your between within subjects variables have the exact same level. But so you can put all the means into a table like that and set your means that way. And that way you don't need to worry about like getting the order exactly right. They're all just named that way. Okay, and now if you have within subject factors, those can be correlated. And it's really important to know, can a label for the y-axis be indicated? Yes, it can, Richard. We will show you, well, I'll show you here. Oh, hold on, no. You mean a label for, okay, because we can change the, what's this called? Like the pre and post. We can record pre and post, and we have pre equals pre-test, and post equals post-test. Like the, what do you want recorded and what do you want displayed? So we have a recording and display for the factor levels, but not the factor names themselves. So then the, these plots will just use that. If you want to change the plot, all this does is output a ggplot, which you can, we're going to get to this later. Sorry, it's not your fault, Richard. I get derailed really easily, but we'll get to it later. All right, so we'll set correlations though. If you've got within subject factors, you can set correlations with R again and do the same, like make a list with cat, dog, and ferret there. So that for cats, the pre-post correlation is 0.5, for dogs it's 0.25, and for ferrets it's 0. We'll set that like that. I think there might be a bit of a bug if you try to do that. Yeah, it gets angry if you set this as a vector, a named vector. It has to be a list. And at the moment, I can't remember why. There's some sort of technical reason why it's tricky. I'll fix it in a later version, but it's hard to fix right now. So just use a list. And for like this, I think you can use a list. Yeah, it doesn't stop you from using a list. So you're fine using a list or a vector for the μ's and SD, but R has to be a list. We can also change the names of the DV column and the ID columns. So the DV column only really has a name when you're in long format. So the data that we're creating right now, pet time, is in wide format. So we've got the ID column, we have our between subjects factor of pet, but our within subjects factors each have their own column. So it's a wide format data set. But we can instead change this to a long format data set with just long equals true. If we run that, same data, but now we have an ID and the within subjects factor column, but now we have a between subjects factor column of time. And then the DV column is always called Y unless you change it. So we can change that and say our ID column, we want to call it subject ID. And the score column, we want to call that, or the DV column that was called Y by default is going to be called score. So run that. We've got a new one called datlong. So subject ID, pet, time, and score. So that's how you can set up the your table in long format, because you often need things in long format for different analyses. And there's a function in Faux to convert from long to wide and wide to long if it's been defined in Faux, because your data table itself will, right, this might not be of interest to many of you, but for those of you who know a bit more about like how the data structures work in R, we've got our data table and it has attributes, and it'll have a design attribute, which keeps all this design information in it. So the data table itself has a design attribute, which it tells Faux how it's been made. So if it's in long format, it will know exactly how to turn it into wide format, like which columns are the DV and the ID column, which ones are the within or between subject columns, so that if you say, convert this to wide format or convert it back to long format, it'll know which columns are which. Otherwise, you can use those functions, but you have to tell it which are the within, which are the between subject columns. So the whole design, and therefore, if you have a data table that was created in Faux, you can, there are ways to grab that design to use to create an equivalent new simulated data table if you don't already have those parameters. All right, so back to here, what are we doing? Oh, right, so if we want to get the parameters from there, from the long data set, we need to tell it which ones are between and which ones are within subject columns, which is the ID, which is the DV column. If you've got a data set that wasn't created in Faux, you have to tell it these things. If it was created in Faux, you don't necessarily have to tell it all of those things, but there's a bug in there. So like one or two of them, you have to tell it. So right now, just like you have to tell it. If your data is in long format, tell it which are the within and between. So I think if we leave that out, what happens? Yeah, it's the same. So you don't have to tell it within, but if you don't tell it which are the between, well, no, it knows, okay. What happens if I don't tell it which is the ID? Oh, if I don't tell it which one's the ID, then it doesn't know how to like group together the within subject stuff. So it just gives you this only between subject. Anyways, best for now to just set all of these when you've got a long data set to get the parameters back. Oh, there we are. Yes, it says right there. All right, if you are teaching or like for any reason, you just want like a real quick demo, a quick data set, you can make anonymous factors. So all this is a between subjects design with 3 levels of the first factor and 2 levels of the second factor, and within 2 levels of the within subject factor. Our muse are 1 through 12. There's 50 subjects. So we just do that real quick and it gives you a plot. And we'll just name these names them A, B, and C. Yeah, so that's a nice quick way to do that. And so this is the plot that it gives you for the design. If you want a plot of the actual data, there's also a plotting function. If you just use plot with the data set, because it has that, the design attached to it, then the plot function figures out like, how do you plot the data? So it'll just give you a plot of the data based on the design that you simulated. So we've got our factors A, B, and C here. If you want the order of plotting, types of GMs that you plot, I can say, instead of doing it in the order that we simulated, so A, B, and C, we want to do B, A, and C. It takes a little bit of trial and error because depending on how many variables you have, it changes which are the facets, which are the x-axis and which are the different colors. If you had 4 or 5 variables, it would look totally different. So the order, you just trial and error. And then geoms, I want to add a violin plot. And instead of this box plot here, we'll do a point range. So the point is the mean and the range is the SD of this. So we could like take out the point range and just do a violin plot, or just do the point range. So what are the geoms that are in there? Let's have a look. Plot dot, oh, was it plot dot faux? Okay, well, there's a vignette about it. Geoms are point range SD, so that's the mean plus or minus 1 standard deviation. Violin box point range SE, so that's the mean plus or minus the standard error. I'm going to add on their 90, like a confidence interval one. Violins box, and then jitter plot. What does jitter look like? Let's have a look. Okay, that you just get a jitter plot, a little cluster of the actual data points. That's just sort of a convenience function, and it outputs a ggplot plot. So you can add stuff onto the ggplot. Let's say I want scale, color, discrete, and I want to change the name of B to, I don't know, B factor. Oh, no, it's going to yell at me. Why? Okay. I need to do that a slightly different way than just replacing the color name, but let's do something easier, like GG title. So you can just add on things in ggplot because it just gives you back a ggplot that you can now mess with. Oh, what's that? Sorry, I'm losing my voice for no apparent reason. Okay. So this is actually a decent point to ask for people to ask questions about, like, so what's going on with these two simulation functions are really the main ones to learn in Faux. Does anybody have questions here about how you simulate factorial designs or specify the parameters? Sorry, I'm looking over there because the chat's over there. All right, well then let's go on to, this is, yes, Richard, this is all for single level data. There are some really basic multi-level data functions in Faux. So if I just pop it, or it'd be easier to see if I put it up here. But they're not like a great solution. Mixed. Okay, so I mainly work with cross-classified designs, so that's all I've really put in here, is a cross-classified design. So if I had like subject n, so 10 subjects, item n, 5 items, random intercept of 0, subject standard deviation, so the random effect standard deviation for subjects of 1, say, and for items 1.5. I'm just making stuff up here. And our error SD. So if this doesn't make sense to any of you, don't worry. But if you work with mixed effects models that are cross-classified and you know how to simulate them, then this would make sense. We'll give this an error standard deviation of 2. All right, what is this? I'll just call that mix demo. There. So that will generate this table for you with your subject and item IDs and your DB, which defaults to Y, but you can change that. It also keeps in random intercept, the subject's random intercept, the item random intercept, and the random error term for each participant, that wouldn't be in your actual data. So you can delete those, but for some sort of checking in stuff, it's useful for that. And if you're also interested in simulating mixed effects models, I've got a whole paper on that. And now I can't remember what the URL is. Sim. Hold on. I'm gonna give you the link for this, but for some reason it's left my head. Oh,
it's
no.
already in the chat, don't worry.
Sim, thank you. Yep, thanks. Okay. And let me see. So simulate imbalanced data set. Yes. Sorry, I probably should have mentioned that before, that like, let's go back to pet time. Okay, so I just never did anything with the n. The n defaults to 100, but we can set the n for cat. Let's do 50 cats, 30 dogs, 10 ferrets. So for your between subject values, I guess technically in order n goes down here, but it doesn't matter if you name them. So there we are. When we get params, then it tells you the, so these are for within subjects. So there's 50 cats, 50 dogs, 50 ferrets, or 30 dogs, 10 carrots. All right. So yeah, so you can simulate for between subjects designs or levels, the different ends. Okay, so because that's one of the most useful things when you're looking at like published work and trying, or kind of post hoc power curves, you've got almost certainly not exactly balanced ends. Can you simulate dropouts so the n is smaller at T2? You cannot simulate that with this, but then you can always go in and wrangle later and change some of them, like, oh yeah, you can. Okay, so we've got pet time there. I made this for Emily Nordman, who wanted messy data. So there's a function called messy. So if we take pet time, let's make a new one, messy pets. Okay, so our pet time, I'm gonna make this in wide format. This will work better in wide format. So pet time has pre and post columns. I'm gonna mess up the post column for dropout. So the proportion of the data that we wanna mess up is, let's say 10% dropout. And then for the post, and then by default, replace is NA. So we'll replace them with NAs, but you can replace them with something else if you wanted to mess them up in a different way. So we'll just leave that as the default. All right, I never use this function, so there we go. Now we've got like randomly 10% of the posts are NAs now. Proportion to mess up, yes. But yeah, so you can mess stuff up if you want. It may not be the best function name, but all right. Yeah, so you can do that. And then anything more complicated, like if you've got more complicated designs, like counterbalance designs, what I recommend is you simulate the full design. So let's say that like you've got people in counterbalance order A and B, and people in A see only cats and people in B see only dogs, or dogs first then cats, whatever. Simulate the fully factorial design and then delete all of the cells that don't matter, that like aren't actually in your design. So right now, Faux doesn't do that. It just simulates the completely factorial designs. And so if you've got a counterbalance design with like some of the cells aren't there, just simulate like a between subjects counterbalancing factor, and then go back in and with your own data wrangling prowess, delete all of the rows that are not in your design. And then if people have really clear design issues, like ways that they can explain how I could generalize this, I'll build it into Faux later. Right. All right, where are we getting on to next? Replications. All right, so this is the fun bit. So here, where we want to start calculating power. What we want to do is simulate a data set like a bunch of times, 100 times or 1,000 times or what. So the sim design function has a lot of checking overhead. Like when you run it, it checks to see if the hour matrix is possible and warns you if it isn't. If you only set one value for SD, it like duplicates it for each of the relevant levels. It just does a whole lot of checking. So you don't want to run that function 1,000 times. What you can do instead, which is a lot faster, is just set rep to a number. There's an argument called rep. So we can simulate a within subjects design with 2 levels, n of 20, mu's of 0 and 0.25, and we can make 5 of them. So like if you want to make 100 data sets that are 200 rows long, doing them one by one, like in a loop, will take like a second or 2 every time. Whereas doing 100 of them all together like this takes like maybe 5 seconds total. So you can save a lot of time with this. There we are, we've got 5 of those. And what that looks like now is a bit weird when you look at it in the environment. So you get a table that says rep, 1 for each, and then data. You can click on the data and look at each individual data set. So you have a table that's got little tables inside of it. But that format makes it a lot easier to run analyses. All right, so there's like even quicker ways to do this, but I'm teaching you a slightly longer way because it expands better. Basically, any analysis that you want to do, you can put inside here. You make yourself a function. We're going to call it analyze. It takes 1 argument, the data set. So we'll just call it data. All right, and then in here, we're going to run our analysis. So what we want, remember with this data set, we've got columns A1 and A2. So we simulate it in wide. So if you want to run a t-test on A1 versus A2, it's paired samples t-test. This is how you would do that. And then you can pipe that to broom tidy. Let's just really quickly here, I'm going to set data equals with this data rep. Okay, so this just takes the data column from that kind of amalgamated table and gives you the first data set. So data itself is that. And that's just so I can test. We have our t-test here. You get that kind of output from the t.test function. That's useless for if you want to do that 100 times, you don't want to look at each of those, right? So you can use pipe it. If you've not used pipes before, %, right arrow %, to broom tidy. That just takes the results of this and sends it to the next argument as the, or to the next function as its first argument. All right, so, and that gives us a data frame that has each of the results values of our analysis. And that's what you want out of your analyze function. You want it to give you a data frame that has columns that are the parameter values and however many rows you need. All right, so we've got this analyze function. When you define it, now you've got a function defined in your environment. And you do analyze data there. If you run that, you just get that tibble back. But we don't need any of this stuff. Once you've got your function defined, you can use this sort of code. You can take the data rep table, all your repeated ones, mutate. So we're going to make a new column called analysis, and we're going to map the data column onto our analyze function. All this does is say for each data cell, each cell in the data column, we want to run the analyze function on it. And the results of that function should go into a new column called analysis. Then we got to get rid of the data column and unnest. So inside of each of those analysis functions, or here, if we would just run this, I assign it something here. Call it sim. We just run that. If you look in here now, this new table, it's replicate 1, we've got our data table, and now you have an analysis table. You can click on it and look. What we want is kind of expand that out, right? So this next 2 lines expand that out. Gets rid of the data column because you don't need that anymore. And then unnest just expands out that analysis column. So if we run that, now for each replicate, we have all of our values from the analysis. So you can basically do this with any analysis that gives you back a data table, and then you can create a simulation table of for each simulated data set that you had, what are the, what's the analysis parameters? And then you can do stuff like check how many of the p-values are less than your alpha, or what's the mean value and 95% confidence interval for your estimate. There's a whole bunch of things that you can do, not just power calculations. You could do things like plotting the estimates that you get, the distribution of estimates. So I'm going to run you through another example here using that same pattern. So again, there's like faster ways to do just the t-test bit, but this pattern works for absolutely anything. So now we're going to, instead of running a t-test in our analyze function, we're going to run an ANOVA. So we're going to simulate 100 of these pet time data sets. We're going to simplify it a little bit though. So we've pre and post for within subject factor, cat and dog for between, 50 cats, 40 dogs. And now we've got this pattern of means. So we've got from pre to post test, there's always, there's an increase. They both increase by 0.2 from pre to post test. And the cat values are 0.2 lower than the dog values. So we've got main effects of pet and main effects of time simulated here, but no interaction between pet and time in our simulation. The effect sizes here are 0.2 because I've set the standard deviation to 1. All right, and then calling the ID, pet ID, DV score. The pre and post are going to be correlated 0.5 for both of them. And we want this to be a long data set because ANOVAs need the data to be in long format. Would it be a problem to run power calculations using the core matrix of pilot data? The correlation matrix of pilot data gives you one estimate of what the correlations are going to be, and that might not be accurate. So one thing that you might want to do is run boundary conditions or a power curve. So you could run your power analysis and say, what's the power that you have when all your other parameters are the same, but you vary the correlation from 0 to 1. Or you can just run like 2 boundary conditions. Well, don't take it all the way up to 1. That's an unrealistic number. But if you say, for my pilot data, the correlation between pre and post was 0.4. But I'm going to see like, what's the power if it's 0.2 and what's the power if it's 0.6? And that can give you a range of what's going on. So assume basically that your pilot data might be an overestimate and simulate something that's a bit more conservative. All right, I'm going to get through this one and then we'll have a quick break and then go into the a bigger exercise. Okay, so back to, so we're simulating this design here, 100 replicates. We run that, our pet time 100. So it's each replicate. If you want to click on data, you've got the structured pet ID, pet time, and score. Okay, and it'll show you the design plot. So you can have a quick look to see, does that make sense? Does that look like what I thought I was simulating? Then we're gonna set up our analysis. If you've never used Afex before, it does a good job of doing ANOVAs the way the SPSS does them, which is not necessarily always the right way. But especially when you're like trying to look at data from the published literature, probably the ANOVAs that people report in psychology papers were done with SPSS using the default parameters. So Afex makes it easy to redo that. We set this value, set some contrast, just because if you don't do it, every time you run an ANOVA in Afex, it will just give you a message saying what's going on with contrasts. And that's annoying. So we're gonna put the contrast, set them manually as the default. And then this option, include AOV, we're gonna set it to false because it runs faster and we're not using the AOV object that comes back. Don't worry about what that means right now. And then we're gonna change the effect size measure. They usually give you GES, but we're gonna use partial eta squared because people tend to be more familiar with that. So we're gonna set that option. All right, so that's just like our upfront, do this once at the top of the script, and now that's going to apply to all ANOVAs that are run with Afex. So we're setting up our analyze function here. This is a little bit more complicated. So again, I'm gonna make data equal the first data set from up here, pet time 100, just so we can run through and test. And I will put that into the chat in case that's not clear what I've typed there. All right, so if we run that, then data is just that table. And now we're gonna, inside this, we're gonna create this analyze function again. So first we're gonna run the ANOVA. If you use a different AOV version from Afex, set it up that way if that makes sense to you. But this one maps on to how we set up data in Faux. So say, what's the ID column? Same as, we set up here. ID was pet ID, DV was score. ID and DV are between subject factors pet, within its time, data's data set. So if we just run that here, then we've got this A object that contains an ANOVA table, and it contains a bunch of stuff that you don't need to worry about. What we're going to do is turn the ANOVA table here. It would print out like that. And we want it, again, to be one of these nice tables. So this is just some code that the ANOVA table is the greenhouse geyser corrected values if it needs greenhouse geyser corrections. So we're going to use the asTibble function to turn that table into a table that contains the row names. What that gives you here, looks like that. You have a column called term for main effective pet, main effective time, and interaction between pet and time. Then you have your the numerator for degrees of freedom, the denominator for degrees of freedom, mean squared error, the F value, partial eta squared, and our P value. And the P value has a stupid name. Capital P R, open parentheses, greater than, capital F, end parentheses. I hate that. So we've got this row that fixes the annoying P value name. In this row, all of this does, it doesn't change the table at all. But if I turn that term column into a factor with the levels of term, then when we process this later, they'll always stay in the same order. Like if you create summary values, otherwise it tries to put them in alphabetical order every time you make a summary. And the alphabetical order is annoying. It's never the right one. So these are just two things that I do because otherwise I find the tables annoying to work with, but they aren't actually changing anything. So we're turning this stupid p-value thing into the column is going to be called p.value. So this just returns that table. We've now got 3 rows instead of the one that we had for the t-test. But as long as it's in a table, that's all we need from our analyze function. We just need to return a table that's got all the values that we want. So let's define the analyze function again. If you don't do that, then the analyze function will be the same as the previous one because you won't have redefined it. Should be down here if you want to double check what you can just type analyze in the console and then it will tell you what's the definition of that function. So we use the exact same code as before. We take pet time, we pipe that into a mutate. So we're going to create this analysis column that maps the data cells onto our analyze function. Get rid of the data column and unnest the analysis. So all that's happening here, pet time sim. So now we've got that table. For replicate 1, our 3 rows, replicate 2, our 3 rows. So then now we can do things like check all the p-values. Or here, yes, so that show you the first 6 rows there. So you can summarize it, do something like grouping it by term. So for pet, we want separate groups for pet time and pet time. And then we can create a column for power that's basically, this is the quick way to do power. You check, is the p-value less than your alpha? So we're going to use a default 0.05 here. But in real life, justify your alpha, guys. So that will give you a yes, no, like a 1, 0. If it's less than 0.05, it gets a 1. If it's greater than 0.05, it gets a 0. And then if you take the mean of all those 1s and 0s, so that's the proportion of them that are significant. So you can do this in a few steps, but this is like the quick way to calculate power if you have a column of p-values. And let's get the mean partial eta squared. And there we are. So hopefully you can see how that extrapolates to absolutely any analysis that you want to do, as long as you can return a data table that has, like, if you just want p-values, you could just return a data table that just has a single p-value if that's all you care about. Maybe you're running a 2x2x3 ANOVA, but you really only care about the 3-way interaction p-value. You could just return that, and that would be fine. You don't need to mess with all of this other data. But I find it useful to show you how you get all of the pieces of an analysis, because then often that leads you to doing things like creating plots of what are the effect sizes that you might find in something like this. All right, bye to everybody who has to go at 2. Was this just an hour, or is it was 2 hours, right? Okay. All right, so again, we see the power. It's smaller for the within subjects factor, or for the between subjects factor of pet than it is for time. And that is the deal with within versus between subjects factors, even though they were the exact same, well, they didn't end up being the exact same effect size, but we simulated approximately the same effect size there. But the within subjects factors, the higher the correlation, the more power you have. So we could go back in here, and instead of the correlation here being 0.5, we could make it 0 and see what happens. So we just rerun the simulated data, rerun this. We don't need to redefine the analysis function, and then rerun our summary. Okay, and now our power for time has decreased. Can't remember what it was before now, but so you can also use this to run like all of it in a loop. So you can vary something like the R. So somebody asked this before, like, what should I use the R for my pilot data? So you run this analysis for 0 and 0.5, or a whole range of values along a plausible range. And then you could put all of those power values together and then plot like your power curve, what happens when you change the R. All right, so there's a whole bunch of exercises here, but we're gonna have a bit of a break and then maybe go on to like a kind of more realistic exercise that I'll explain later, but we're gonna replicate a published paper that looks at how plausible is it that you would get 6 out of 6 studies, all 6 of them would give you significant results. All right, so I'll be around while we have, let's have a break until 1/4 past, so like 7 minutes. But if people have questions, I'll still be here.
Okay, great, thank you. So quick coffee break and we'll get back to it. Thanks.
All right, Ahmed, the data simulation for regression analysis. So sim design is really designed for factorial designs, where you've got categorical within and between subjects factors. So if you don't have any categorical within and between subject factors and like everything's continuous, then you would use Arnor Multi. If you also have you have a factorial design, but it has some covariates. There's a few ways to do that, but I think one of the, okay, I'm gonna pop to the bottom here and, okay, so we have that. I'm gonna grab that pet time example again, just like a random one. Okay. Okay. So this is just like, I'm not setting any parameters here, but pet time looks, where is it? That one? No, that one. Okay. So we've got our pre and post. And let's say for each of these, we want to add on a covariate, like the pet's age. I don't know. You can add on to here. Let's say we want the age to be correlated with pre and post in a certain way. So you can pet time age. And this is called Arnor pre. So we want to say that either the existing vector, if you have a vector of just one, or a data table of all the vectors that you want to make this new variable correlated with. So let's make it correlated with both pre and post. So we have a data table. Let's grab, what is, I never remember how to do this. You know, let's do it the tidy way. Select from pet time, pre and post. So you need to have a table that has just those variables. Okay, so x equals that. And then we need to say, what's the mu, the desired mean of our new vector? So let's say the mean age of pets is, I don't know, how old do pets get? 7 years. SD of 2, I don't know here. And R, how do we want it to be correlated to all those things in X? So let's have the age be correlated to pre by 0.2 and post by 0.3. Again, these can be these can be impossible if sometimes they're impossible and you'll just get a warning that says there is no possible vector that is correlated in this way to these two existing variables. All right. Go. Now we've got pet time now has age attached to it. Also, we might notice here that okay, we've got age and it's, maybe we want to further make that round it to the nearest integer. Or maybe, so we don't have any impossible values here. But let's say if we increase our standard deviation, it was actually 3.5. I bet we're going to get some negative ages. Okay. You can also transform values. There's a function in Faux. It's called norm2. And that transforms the normally distributed variable to some other distribution. So you can transform things to a beta distribution, binomial, gamma, Likert scale, Poisson distribution, but here we're going to do trunk norm. So I'm actually going to do this before I round them. So norm to trunk is going to be, it'll take that vector. What's the minimum of our truncated value to return? Let's say animals can't be younger than 0 years, and they're not going to be older than 12. So our max will be 12. Because because sometimes you've got a restricted range of what you're trying to simulate. And so then we'll also afterwards pipe that to round to just round it to the nearest integer. So then this will make sure that all the variables that you get back are within that range. It takes the entire distribution and recalculates it. So it doesn't just like cut off the ends or squash them back in, but it'll change all of the values to make sure that the returned vector has the same mean and standard deviation as it did previously, but doesn't go outside of the min and max. All right, I'm gonna go on to some other questions then. Yes, so Ominia, at the moment, all we have are these norm 2. So if we've got like, let's our norm 100, 0, 1. Okay, so we're gonna like generate 100 values from normal distribution between 0 and 1. And I'm gonna just make a quick dumb histogram out of them. Okay. Let's just pop that here. Okay. So we can use the norm 2 functions. So like the binomial distribution. So we can say the size. So let's say actually we've simulated a normal distribution, but your data are how many things that people got right out of 20 trials. So they'd have a size of 20. And then say the mean probability that they get it right is 75% of the time. And then you can set the mean and standard deviation of the simulated data, or it can just read that. You don't need to set the mu and SD here. It'll just set them to whatever the mean and standard deviation are of the vector that you fed this function. So we can, so now this has changed those 100 values into values that can only be integers 0 through 20. And if we change the probability to 50%, so people are kind of at chance on this. Now we've changed our distribution to look like that. The other functions, so if you want a skewed one, I don't have a good function for inducing skew right now, but beta can kind of get you there. I can never remember with the beta function, like what shape 1 and shape 2 really mean. But let's say they're non-negative parameters. Let's just set them at 1 and 3 and see what it looks like. Okay, so yeah, you can, what happens when I make that one big? Oh, that skews more to the left. What happens if that one's big? Right? Ah, okay. Anyways, this is doing beta distribution stuff. Somebody asked me for a beta distribution converter. I can make one, but I don't know much about the beta distribution myself in terms of like, how does it map onto skew? All right, so we end up with a kind of uniform distribution between 0 and 1. If we've got these both 1s, they have to be positive. Ah, okay. Anyways, so it's up to you to figure out what the beta distribution does. And if you have suggestions about like transformations that you think would be useful to build in, these functions are pretty simple, actually. Like the function itself is 2 lines. It takes the normally distributed vector x, calculates its mean and standard deviation, or you can input those, and then uses the p-norm function to give you the percentile, basically. Like, is percentile the word that p stands for? It isn't. But anyways, uses the p-norm function to tell you like each of those values is in the 1st percentile or the 50th percentile or whatever. And then uses the q function of the new distribution that you're converting to convert that. So basically, yeah, puts it into a uniform distribution, then converts back from the uniform distribution to the distribution that you are targeting. And then you need to add whatever parameters that that new distribution needs. So you can write your own functions like this. But let me check, where are we? We're way past the end of the break. I'm gonna skip over mixed model stuff, and I can talk about that afterwards, but yes, the item random effect of omega is the item SD in that function. I didn't know about the Pearson DS. Thank you, chat. And hang gamma. Do we have R to gamma? Yep, we have norm to gamma. You can use the gamma distribution. So you just need to put shape and either rate or scale in as parameters. All right, so for the rest of this, there's like a lot of exercises here that you can do to set up, to like practice setting up things in Faux. But what I thought would be more interesting is if we used from DSW exercise calories. So pop that into the chat, but also if you need the, oh, where'd it go now? There we go. Also, if you don't have the DSW package, there's the direct link to the code. All right, so this is a really cool paper. I'm gonna restart my R session to get rid of everything environment. You can do that. I've got a keyword shortcut for it, but under the session, restart R. If that hasn't cleared your environment, you need to sort out your preferences, or well, what is it? It's under global options. If you go into global options general, do not restore our data into workspace at startup. Never save workspace on exit. Apply that. Get rid. You don't want your environment sticking around between sessions. It's a terrible idea. But or you just clear that little broom. Use the little broom to clear out your environment. Okay. So we're starting over. Calorie placement, resimulation. Here we're using tidyverse for a little bit of data wrangling. Faux, AFX for ANOVAs. EM means, which should have downloaded with AFX if you have that, for contrasts, so ANOVA contrasts. We're going to set Faux options to not plot stuff. So you know how when you simulate stuff with sim design, it always generates a plot. I find that really useful for sense checking my plots, but sometimes you just want to turn that off globally. So that's what this Faux option does. Okay. So Francis and Thunel have a paper in metapsychology this year, or last year, reanalyzing data from Dallas, Liu, and Ubel, who showed that when people look at a menu, if the calorie count is on the left of the item, they order items with fewer calories than if the calorie count is placed to the right of the item, or if there's no calorie count at all. All right, and then, so they replicated this in 6 studies. One of them was in Hebrew, where they showed that because they read right to left, that if it was on the right, you ordered fewer calories than if it was on the left. So whichever side you get to first when reading is their hypothesis. Francis and Thunel thought this sounded suspicious, and that actually, given the number of participants in their studies, it was pretty unlikely that if you ran 6 studies with that power, that all 6 would end up significant. And to really demonstrate this, they needed to calculate the power for each study. So this is one place where calculating post hoc power is useful. So there's some links here to the reanalysis that's on metapsychology. Their code is extremely efficient. It's harder to read, and it doesn't use Faux. They simulate data in a different way using basically what Faux uses under the hood. but you can go through their code as well. And then there's the original papers. Table 1 of the reanalysis paper provides all the parameters that we need. So basically, for every study, it's just a between subjects study where some people got calorie replacement on the left, some people got it on the right, and sometimes some people got no calorie replacement. So we have a between subjects factor of calorie replacement, and then they just ran t-tests or ANOVAs to test their hypotheses. So we're going to run this as well. Oh goodness, this is the one that doesn't have data in it because we were going to do it together. Okay, so let's do it together. Let's see if I can actually live code this. So study 2 is a t-test, easier to do, so let's start there. We're going to use the sim design function to create a data set for this study. Okay, so again, we have between subjects factor. So we're going to make a list with what's our one factor name, we'll call it placement. And it has levels left and right. All right, and so we have the ends for left is, what is it? 143 subjects on the left, and on the right, 132. If we keep these in the same order, we don't actually have to label these left and right, so I'm going to quit doing that. Our mu, our means, on the left side is 1249.83, and on the right is this number. I'm going to copy paste here. And standard deviations of okay, it's between subjects, so there's no correlations here. And yeah, that's fine. Okay, so we can run that, have a quick look at what the data table looks like. We've got ID, placement, and this is how many calories people ordered. So let's give the DV a better name, like calories. Okay, so we've got our 275 subjects, some on the left, some on the right, and simulate their calories. Then we're going to create this S2 analyze function. So remember, we're going to simulate that data set. And we're just going to do a t-test. So while we're developing it, we can just work on this S2 data set. S2, we just want to calories. Are they different depending on placement? Get back up here. Placement. Our data is S2, so let's just check that. So mean left is lower than right. P-value is 0.065, whatever. Remember, we want this to be in a data table. So we can use Broom tidy. And that gets us our estimates and our p-value, etc. So we're running this on data S2, but because this is wrapped inside of a function, our data is actually going to be called data. I just had that as S2 for testing. So we define that function, our S2 analysis function. There it is. And then we can test it. We run it on S2 because it's only one data set up there. All right, that works. Now that we've got it working on one data set, we've got to make 1,000 data sets, which should be, oh, thanks, Kate, or thanks, Jen. Ah, Sao Chin, thank you. Okay, so make 1,000 data sets is no harder than copying that and put wrap equals 1,000. Run that, takes a few seconds. come on. Shouldn't take this long. Okay, there we go. Maybe you put in 100 if your computer is slow. But so we've simulated data 1,000 times. We've got 1,000 observations, S2 here, and it just looks like that. Okay, and then we run the analysis on each set. So we can go back to the Faux stub under the ANOVA title and just grab that code. Okay, so our S2 sim is going to be, we'll start with this S2 data set. We pipe that to the mutate. So we're making a new column called analysis. And it's just going to be, for each row, you're going to take the value that's in the data column and run the analyze function on it. Then we're going to get rid of that data column and unnest. We do this exactly the same every time. So I think I'm going to write a new function in Faux that you just tell it what analysis you want to run on what group's data set, and then it will just give you this. So you don't have to write this code all the time. But for now, just learn how to write that code, and it's always the same. All right, so, and I will pop that into the chat in case people need it. So run that. Object analyze not found. Yep, that's because it's called S2 analyze. All right. So yeah, pay no attention to the stuff I've written there. There we go. Okay, that's the right one. Okay, and then this just gives us the first 6 rows. So we've got our estimate of the difference score, or the difference between the two, estimate of left, estimate of the right side, and then our p-value. In high and low confidence intervals, you can do all sorts of stuff here, but all we really want to do is summarize the p-value column, right? We just want to take that table. We don't need to group it by anything. We just summarize this p dot or power equals mean p dot value less than, we're gonna go with the 0.05. And I'm gonna pipe this to pull power. All that does is just takes, this turns it into a table. Let me show you there. So that gives you a table with a column called power in this value. And if you pull the power value, it just gives you the value itself, since there's only one. So we're just gonna set this variable S2 power to power. So you should get not an identical number to me, because we don't all have the same seed. We don't have even set a seed on this yet, but it should be pretty near 0.5. And the value in the paper, 0.54. So we're pretty close to, they used the analytic function. So you can just use the equivalent to G power, which the, oh goodness, I don't have the power package right now. I've recently updated my computer. But you could use the power package to calculate that, like from these values alone. You don't need to do this by simulation, but we're practicing here. And also it's an unbalanced design, which are slightly more difficult to do. Let's see, somebody's got an object S2 sim not found, okay. So what's happened before? So do you have S2 and S2 analyze in your environment? Because if you set up S2 analyze, you could have, like, I popped that into the chat as well. If you have this here, but you haven't run it yet, so it's not a defined function, then the rest of the code won't work. So that's the first thing, is to check that that function is working. But yeah, just put in the chat if it's still not working after you do that. But if we go on now to something where the reanalysis paper also had to run a simulation because there's no way to do an analytic power calculation, is study one. So again, if you've got this outline here, you just click on study one, pop it down to where we are. So study one has no label condition. So there's a more complex decision rule that the left side needs to be lower calories than when it's on the right side, and also lower calories than when there's no calorie information. So they ran an ANOVA and looked at the overall effective placement. If that was significant, then also the the contrasts between left and right side need to be significant, and the contrast between left and no label need to be significant. So all three of those things need to be significant to support their hypothesis. Right. But let's first do the simulation itself. We can kind of copy what we have for study two here. It's a pretty similar design. Study one, but we have left and right and none. You'll need to pop right up to the top and go into the reanalysis paper. So this is free online, but this is how we're gonna get. Okay, and then you need to download the PDF. I don't know why it's, and then table one, pop over here. Okay, so this is that table one. Can I make it bigger? Yes, I can. All right, so we're gonna get our data here for study one. I move that up here, move this down here. Okay. Yeah, study one. Okay, so we have left, right, none label. And so we need our ends. So there were 45 people in the left condition, 54 in the right condition, and in the none condition, there were 50. We got the muse, 654.53. This feels like excessive significance here, or significant digits here. 865.41, 914.34. Yeah, I don't think 0.34 of a calorie really is going to do much here, but standard deviations 390.45. I'll put this in the chat after I type it up. So 517.26, 560.94. Oh, 560.94. Okay, so we've got, so simulating the design itself is pretty straightforward. We'll just do one to start with. In fact, right now, let's call this data so we can, when we design the analysis. Okay. Just in case you don't feel like typing all those numbers yourself, it's in the chat. Now we've got to set up the analysis. And this is mostly done for you because it's a little bit more complicated. We reset the sum contrast and avoiding the annoying message on each run. Here we do need to include the AOV because we need that object inside the analysis to run EM means. EM means lets you do the planned contrasts. All right, so our data analysis function, so everything that's inside of here. We run our ANOVA on our data. So ID of ID, our DV is calories, the between subjects factor still placement, data is data. So this is the same as before, or not before, but so we've got our ANOVA. If you just type A in the console, it'll give you some output here. So our effect of the main effect of this placement variable. And then we need to run contrasts. So to run contrasts, you need this line, E equals EM means A of the, so we get the estimated marginal means for the placement main effect. And then we need to set up our custom contrasts. So this is our left versus right contrast. We think that the left value is going to be lower than the right value. So we set left value of -0.5, the right value of 0.5, and we don't care about the no value. And then we also think left is going to be less than the no label. So left is negative 0.5, no label's 0.5. We don't care about the right label. So here's our two contrasts set up, and then you run the contrast with the contrast function. So you run the contrast on the EM means with the C1 contrast. I'm not sure if this is right in terms of like, what did the authors do in the paper? Did they use corrections? And if so, which corrections did they use? So I'm just using Holmes corrections to adjust for multiple comparisons. I'd have to read the paper more closely to see what the actual authors did. But if we run that, so let's run that, this, and that. B is now a table with our two contrasts, their estimate, standard error, degrees of freedom, and then adjusted p-values. We only really care about these p-values for the task we're doing today. So what we can do is just make a data frame. So our analysis function returns a data frame that's the p-value from the ANOVA table. So our overall main effective placement, plus the first adjusted p-value from this contrast table, plus the second one. So that data frame here looks like this. 1, 2, 3. So we just get back the 3 p-values. We could have returned all of those values if you wanted to do things with them, but we don't. There's nothing more we're going to do with the other values today. So let's set up this S1 analyze function and run it on data here. Because remember, we named this data so we could.
Morning over here.
Mute. Yeah, I don't think they meant to.
I think it might be an accident, yeah.
All right. Okay. So we've created our analyze function. We've run it on data here just to double check. Yes, it worked. So like before, we're just going to go back and copy that. So S1 is going to be this, but we're going to repeat it 100 times. Let's just do 100, not 1,000, because it'll take too long to run. Okay, so we've run it. That went really quick. And then S1 sim, same thing. We'll go back to study 2 and grab the same, run the analysis on each. Now in study 1, run the analysis on each data set. So we run it on the S1 data set, and we run S1 analyze. So they each have their own separate analysis function. Now pop that into it'll take a few seconds to run because we're running 100 ANOVAs and then 100 contrasts. It doesn't take too long. All right, so we've got this table here, S1 sim. It's got 3 columns for each of the p-values. Now we need to turn those into like a yes or no decision. Did this support the hypothesis or not, so that we can calculate power? So if we want all 3 p-values to be significant, let's pipe that to mutate. If it's significant, if, what would we call these? P underscore all. So we want P underscore all less than 0.05 and P underscore 1 less than 0.05 and P underscore 2 less than 0.05. I don't think I really need these parentheses, but they will maybe make it clear what we're doing here. Okay, so this is basically it's significant if all of those are less than 0.05. So run that. What we get back here is a new column called sig. So yes or no, and then I recommend building up your analyses like this so you can do some sense checks. Like that one's not significant. These we've got That's 0.08. Does anybody remember how you turn off the scientific notation? It's like options, digits. Okay. Nope. SciPen. Does it have to be 999? 6 is working okay. All right. It makes it slightly easier here to do your sense check. Okay, so that's false because yeah, these aren't all significant. Not all significant. And then this one's true. Yes, these are all significant. Okay, we've got our significance column correct. Sense checks are always good. Now we'll summarize. So power here is the mean value of sig. So falses turn into zeros if you try to calculate the mean, and trues turn into ones. So the mean is what proportion of them are true. It's just like a shorthand way to, we don't need to convert them into zeros and ones. False and true turn into zeros and ones when you try to do a mathematical operation to them. And then we want to pull the power column again. So do that. S1 power is 0.44. In the paper, they got 0.45, so it looks like we're doing okay here. All right, so study 3, we can use like the exact same pattern from study 1 to analyze the data from study 3. We just need to sort out the data set. I think I'm not gonna do these with you. So for study 3, the only difference is you need to redefine the analyze function because your contrasts are right versus left and right versus no calorie placement. And right is predicted to be the lower of those because in Hebrew, people read from right to left. And then there's studies S1. So you can, that's a same pattern as study 2. It's just a t-test with right and left. So you can just reuse the analysis function S2 analyze. Study S2 is the same pattern as study 1, so you can reuse the S1 analyze function. You don't need to redefine that one. And study S3 is also that same pattern. All you really need to do is redefine the data based on this table. So you've got the left, right, and no label, mean, standard deviations, and ends. You calculate power for each of them, and then you multiply all those numbers by each other. And that will give you the probability that all 6 of them came out significant by chance alone. Because if you run a whole bunch of studies and you don't have very high power, it's really unlikely that everything's going to be significant, even if it's a true effect. If you want to see this worked out under the website, the DataSim website, there's the calorie placement resimulation, and all the answer code is in here. But I would recommend that you try to do these other 4. We've gotten the first 2 down. That gives you really the whole pattern. Study 3, you need to recreate the analysis function just because of the different contrasts. And the other ones, you can just reuse old analysis functions. So we'll just do the last few minutes for general questions.
Thank you very much, Lisa. That was actually absolutely amazing. Yeah, does anyone have any questions about Faux at all? A lot of that stuff just completely blew my mind because I do things like in base R, and that was just.
I can show you a really quick. Okay. The Faux website itself shows you all the extra things that Faux does. So I've only given you a pretty basic introduction today. But there's the simulate by design, which we did today. This shows you a bit more of like, because we only did one between and one within subject factor. It's a little bit more complicated if you have multiple between and multiple within subject factors, like how do you specify different means for everything? But the website gives you help on that. You can simulate from existing data if you just have an existing data set. like the cars data set that's built in, you can use the sim_d app, so simulate a data frame, and it will just simulate it for you. If it has any between subjects variables, you have to tell it which ones are between subjects variables. And what else in here? If you have continuous predictors, so somebody was asking about like for regression designs, and I think what they meant was designs that have covariates. You can, this shows you how to do one or multiple continuous predictors using sim design. You could also use Arnor Multi if you only have continuous predictors, or adding in continuous predictors to a factorial design, which I went through a quick demo of that, but this gives you all the details. There's all the various plotting functions, like how it plots things with more factors. The mixed design simulation, which is still really, really basic. The distribution conversions, which we talked about. So it gives you plots for all of the, you can translate from normal to other things or other things back to normal. And I'm going to talk about codebook. Okay, so we've got the OMID. In the last example, why did we count the number of p less than 0.05 when all the effects were significant? That's because the criterion that the authors of the original paper were using for was their hypothesis supported was that all three of those things were significant. So what we were doing for a power calculation is like, in how many of the simulated data sets did we also fulfill the criteria that the authors had for supporting their hypothesis? So significance isn't always like just one factor, like one p-value isn't always the thing that you need to give you power. Sometimes it's, you've got a more complicated decision rule about whether or not you're going to support or refute your hypothesis. And that's another reason that like simulation is incredibly helpful, because there just is, G-power is never going to do that for you. G-power might give you the power for one of those, like for the overall ANOVA effective placement or for the contrast, but it won't show you that, like, because those things will be correlated. If the overall effect is there, then the contrasts are more likely to be significant. So if you have anything that's in any way not fitting in with something like G-power or the power package, or the analytic ways that you can calculate power, then simulation is really your only option. Right. Any other? Oh, that's lovely, Sarah. It feels, I'm glad that you think the package is great. It feels like a big responsibility to have created a package. If people are going to use it, then it better be right. And also, none of you better use it for evil. We talked about this a little bit right at the beginning, but yes, please, nobody simulate data for fraudulent purposes. Because I know this, it gives you data that's too perfect. Real data don't look like this. They don't come from perfectly normal distributions. And you can, like, the messy function lets you mess them up a bit, and you can convert them to have some skew, but they've got perfect skew then. They're like, follow a perfectly beta or gamma distribution. So again, so that's a tricky thing about simulation. We're simulating data here from idealistic populations that have perfectly normal distributions, and you know that your population does not have this. So the further development of Faux is going to be to help make it a little bit easier to figure out what, deal with Likert scale data. We have that function norm to Likert, so you can simulate normally distributed data and then convert it to fit a Likert scale distribution where 1 has a 10% probability and 2 has a 20% probability, whatever. But this is kind of meant to just get people started and to be able to kind of quickly prototype simulations. Whereas if you learn like the base hour ways, you can often do them a bit faster. So if you're wanting to run 1 million simulations, Faux might be a lot slower than programming it yourself from the bottom up. But if you're just getting started, I hope it's helpful.
Absolutely. There was one other question about whether there's advantages to using tidyverse for simulation.
Tidyverse, I use the tidyverse for data manipulation because that's what we teach at Glasgow to undergrads. So it's like familiar and consistent. If you use other methods, go for it. There's not really a big difference. Tidyverse of, if you use kind of like tidy everything, then your data frames will work with each other and with these functions really well. So, I use the map function from the per package instead of lapply. When I'm running code like this, when I write packages, I actually use base functions more often because they can be faster. So work with really what's familiar to you. 1 million simulations will blow your laptop up, I think. Yeah, it depends on what you're simulating. Like it's pretty trivial to run 1 million t-tests, but 1 million mixed models will not finish running till the end of time. All right, let's see. What to interpret from the power equals 0.4 in the calorie example. So those are the published studies, Samara. We're using the means and standard deviations and the ends reported in the published studies. So that is their sort of post hoc power, that if the effect size that they found, that they reported in their sample, is the population effect size. And we don't know for sure, like, is it an overestimate or an underestimate or what? But given the effect size that they found, that's the power that their study had to detect an effect of that size. So like the conclusion of the reanalysis study is that these are really unlikely to be, let's say carefully here. They're unlikely to have been the only studies that were run. So it's likely that they actually ran a bunch more studies and only reported the 6 significant ones. I think nobody's really accusing anyone of fraud here, but perhaps selective reporting. So the whole point is that, yeah, if you run a bunch of underpowered studies, it's actually less likely, even if the effect that you're looking at is real. If your studies are all underpowered, it'd be really unusual for all of them out of 6, say, to be significant. All right.
Hello.
And you do go ahead and send me emails. Well, actually, tweets reach me better than emails. I'm on Twitter at Lisa DeBruine. So thank you all for coming.
Well, thank you so much, Lisa. That's been absolutely amazing. And we'll see everyone, the next session's on Monday with doing stuff like this, but from like first principles using Arnor and things like that. So some might not even need it. It's just kind of like a sort of basic example using t-tests. And sorry, I was looking at my screen. Okay, thank you very much. And yeah, we'll see you shortly. Bye.
Oh, that was fun.
Yeah, no, thank you. Yeah, that was, yeah.
Did you get the recording off?
Oh, that's a very good point.